We attended a seminar today at the physics colloquium series at Berkeley. It was about cosmology and AI, and it's interesting because it shows how AI is infiltrating physics, and it also helps understand how physics is helping AI. So the lecture by Professor Uroš Seljic, a professor of cosmology at Berkeley, he is pretty instrumental in collecting data and analyzing the data. So this is what cosmology is all about. Cosmology, the way I can see it from the outside, it really reminds me of economics. So you have this, macro system, a large system with lots of data, and what you're trying to do is find systematic relationships within the data, patterns, things along those lines, to build a model and then go back and look at initial states and then use the model for inference and then see if you can match what you see. So similar to economics in the sense that I asked one question, for example, I asked, how about interpretability? And the answer was, look, we don't really care too much about interpreting stuff here. We're really at a point where we just want to be able to predict stuff, see what's in the data, and find relationships and then predict stuff. So we're kind of in the early model stage. If I want to use, David Deutsch here, theory versus observation, we're definitely in the observation phase here. So we're in a state of phase where we just look at the sky, we collect data, and then we try to figure out stuff. So it's in that sense, I would say it's not an interesting science. Why is this relevant for us here at Orange Capital Partners? First, of course, it helps us understand where influences come from in the AI space. So, for example, understanding data and, in particular, being able to analyze data with less compute power is one of the problems that cosmology has. Cosmology has the amount of data that is collected is gigantic. So one of the problems that they're doing, or one of the solutions that they see is to I don't know what the technical word is. It's basically get rid of redundant data. Okay, so let's say you have a tree, and it's a very dense California tree. You have a lot of green in that tree. You don't need all the green pixels of the tree. All you need is the edges, and you can find that by using differences. So this is, convolutional neural networks come from that area. They look at certain areas of the tree, and as long as the difference in value of, let's say, a certain pixel is the same, that means it's green. And as soon as the difference is above a certain threshold, that means that there's an edge. So maybe we should incorporate that data in the analysis. So it's something along those lines that the professor was talking about. Basically, what the lecture was about is how AI is influencing physics and how physics can influence AI. And I think the learnings are that you have a lot of statistical modeling, a lot of mathematical modeling that comes from physics and actually influences AI. And then, of course, AI can help analyze physics. So this is Not Even Wrong podcast. It's September 11, 2023. This is Krim Delco. For the day, the fund is up 21.5%. The market is up 67 basis points. For the year, we're up 135.7%. The market is up 16.2. We're outperforming by 119.5%. I think just real quick about the outperformance, we had an upgrade by Morgan Stanley for Tesla. This is one of the drivers, but I haven't really analyzed specifically what drove the stock today. So I'm going to do this tomorrow or pretty soon. I want to focus on the seminar today because let's just calibrate where we're coming from. Okay, for new listeners, why are we talking about physics seminars? Why are we going to universities? Why are we attending seminars? The fundamental idea here is that the same way we read books, we also we go to conferences, seminars, particularly our proximity to Stanford and Berkeley, location-wise, allows us to, sneak peek, go in there, see what's going on, pick up some nuggets here and there. The idea is really to try to understand what is driving science, where is science today, and what can we expect from science as far as technological applications are concerned. This is the fundamental idea. It's like a lot of times you have to dig for a lot of dirt and in order to find some nuggets. Now, going to Berkeley or Stanford, I can assure you that you don't have to dig too much dirt, that there's a lot of nuggets there. There's a lot of intelligence, a lot of interesting people are there. Last Friday, we attended a seminar where we spoke, the professor there, Professor King, electrical engineering at Berkeley, spoke about the need for innovations in semiconductor technology. She particularly presented her ideas of mechanical gates. And the idea there is that if you have digital gates, you need a certain amount of voltage to make the change from, let's say, to flip from up to down or something like that, and that minimum voltage is relatively high, so you need more current, that is more power consumption, etc. If you can do mechanical gates, you can do a lot less voltage, you need a lot less current, and therefore you can save power. That's the idea. I think it's a beautiful example of how engineering can help solve problems in semiconductor technology. Now let's get back to today's seminar. It's how does AI influence physics and how does physics influence AI? I think it's a very interesting circular reference here. Let me just set the stage. So the professor, Seljuk, is a cosmology professor. And cosmology is very similar to economics, where you look at a massive macro space. In this case, you look at galaxies, you look at stars, all that kind of stuff, and you collect a lot of data. And the idea is, can we find, excuse me, and we have a model, right? So the model is like we think we understand, or we try to understand how the universe is evolving. What are the parameters that are driving the evolution of the universe? And we look at the data, and what we're trying to do here is we're trying to find relationships in the data that we see, fit them in the model, and then do back inference and see what we actually observe, and if you see if there's a match. And the better the model is, the better we can calibrate the parameters, the closer we are to finding what's really going on in the universe. Now, you can argue the purpose of this is maybe a bit questionable in the sense that, do we really need to understand what the rate of acceleration of the universe is? Do we need to understand what dark matter is? The answer is yes, we do, because that's what science is really all about. And maybe we don't see a direct application today, but I can guarantee you that we're going to see some applications coming forward. Like everything else in science, sometimes the ideas are a bit far-fetched until they're not, until all of a sudden there's an application that changes everything. So anyway, but back to AI is influencing physics in the sense that we have machine learning, we have statistical analysis of data that helps us build those models, calibrate those models, estimate those parameters, etc. Now, how does AI influence physics? How does physics influence AI? Well, it's a circular reference, which is that you also have applications coming directly from physics. For example, stable diffusion is working with Markov processes, for example, which is a physics concept used in many different areas of physics and engineering, and it's also being applied in computer science. So I think I was talking to my partner Zubner about this. Okay, what is actually the role of physics here when it comes to AI? And the role of physics is to use mathematical models to try to understand how to analyze data. In particular, for example, how to reduce the amount of data that is being analyzed to still have good results. That's one of the things that was presented today. The names don't really matter. Fine-grained Monte Carlo, things along those lines. It doesn't really matter what they call it. What matters is more the big picture, which is you have models, probabilistic models, stochastic models, nonlinear situations that you somehow need to make sense of. And particularly in cosmology, a lot of things are nonlinear. So what that means, you do point-to-point analysis, and that's Markov chains. So you take point A, and then you take point B, and you see, okay, how do they relate, and then how does B relate to C, and then how C relates to D, and then maybe you can connect A to D, maybe not. Maybe it's a step-by-step model. Maybe it's some sort of function, long-term model, things along those lines. That is, of course, way too much detail for me to present here. But the point, again, is that you have a lot of innovations on the physics side as far as mathematical modeling is concerned, computational modeling, that then goes back to the comp sci people. Let's say people like at OpenAI might take these models, try them out, and what they do, what they particularly do, let's say, what's the role of a comp sci person? Well, they will try to program this or build infrastructure for this. So again, that they can optimize, let's say, for power usage or compute or storage or all of the above. So to summarize, the application of AI in physics is it's open, it's there. We have discriminative models, so things like, okay, is this a cat or not a cat? And we have generative models, which is we look at data and try to generate something out of it. So we have both applications very broadly used in physics. And like, I think physics is maybe the mother of all sciences, but it's being used everywhere else. It's being used in the social science, being used in chemistry, in engineering. And this, of course, goes back to our investment in NVIDIA. It's been probably about 6-7 years that we attended GTC when all of these things were presented, maybe the first time in the context of GPUs and parallel compute and accelerated compute. And now this is definitely taking off in a much, much broader way. I think I also want to mention the reverse, so the influence of physics in AI. I think that's important, that you have a continuous research and development on the mathematical, statistical, and physical side, and make better models, make better mathematical approximation, particularly, again, in trying to understand what data is it that we actually need to analyze and what data can we disregard. Thank you.